Right. Today we are going to be analyzing polynomial functions. We've been solving polynomials, finding their zeros. We did some graphs back at the beginning of the unit where basically we just used our calculator and made some guesses. We had points on the ends and we had some points where it changed direction. Today we're going to get much more specific with our graphs. So our first learning goal is that we are able to identify what are called turning points as well as intercepts of a polynomial function, and that we are able to produce an accurate polynomial function graph using our technology. So before we get into our examples, I just want to talk about this polynomial that I've already got graphed on here for you and just talk about the different important features that you're going to be identifying and what those look like on a specific polynomial. So important features of a graph in no particular order. One of the most important features of a graph are the x-intercepts, or the zeros. So in this particular case, the x-intercepts, if we look, we see an x-intercept here. So there's an x-intercept. Here's an x-intercept. And here is an x-intercept. So, we can see that we've got, one of them looks like it's at -3, and the other two are definitely in between. So we're not sure of those values. So it looks like we have an x-intercept at -3, 0, plus two others that are unknown right now. Other important features of a graph, other than the x-intercepts, are what are called turning points. And we haven't used that vocabulary yet, but we have done this type of identification before, because a turning point is just where the graph changes direction. So we'll write that down. Turning points are where the graph changes direction. And we have two types. And this vocabulary is going to be very important too. In calculus, you use this all the time. Two types of turning points. One are called local minimums. The other are called local maximums. And all that means, a local minimum just means it might not be the very lowest point on the graph, but it's the lowest point in that area. So I call the local mins the valleys, because it's when you've got a down portion of the graph. Local max, I call the hill, because again, it might not be the highest point on the entire graph, but it is the top of that particular area. So local mins are your valleys, and local maxes are your hills. So if I'm looking at this particular graph, I see that I have a local minimum right down here, because this is a valley. So that's what a local minimum looks like. I also have a local maximum, because I have a hill right up there. So x-intercepts are important, turning points are important, and then something we have studied previously, end behavior is important when we're talking about a graph's characteristics. So remember that end behavior always starts as x approaches infinity, f of x approaches blank, and as x approaches negative infinity, f of x approaches blank. Now remember that this first part, as x approaches infinity, means as you go to the right on the graph. So as I go to the right, this, and I didn't draw arrows on the graph because I couldn't get it with the tool I was using, but there should be arrows there. As I go to the right, this graph, this arrow is going up. It's going to positive infinity. So that should be positive infinity. As x approaches negative infinity, that means as I go to the left, what's happening? And as I go to the left, you see my arrow is going down. So in this case, it's going to negative infinity. These are your dance moves, remember. So this function here, because of its end behavior, we can say that we know, even though we haven't seen the equation, we know that this particular function is positive with an odd degree. So positive, odd, dance move. All right, so those are the things that we're going to be focusing on, and now we're going to look at some examples of some specific functions. So the directions say graph the function after filling in the important information. So notice it says after filling in the important information. So you fill in the information first, and then you use the information to produce your graph. So, how many roots does the function have? Well, we learned in section 6.7 from the fundamental theorem of algebra that whatever the degree of the function is, that's how many roots or solutions it should have. Now, because this is written in multiplied form, you might not know right off the top of your head. You might have to think about this for a second. If I FOILed this back out, x squared times x would be x cubed. This x squared times 4 would be positive 4x squared. In the middle, negative 9 times x is negative 9x. And negative 9 times negative 4 is negative 36. So if I multiply that out, I could distribute the negative 2, but I don't need to because that's not going to change my degree. My degree here is 3, which means this function should have 3 roots. Now, here's a neat trick. Turning points, and you'll want to write this down somewhere, turning points cannot be more than the degree minus 1. Now, we will actually want to look at the graph to see how many turning points this has. But I can say since my degree is 3 minus 1 is 2. So this function can't have any more than 2 turning points. So if I look at the graph, again, I'm not graphing it my exact graph yet, but if you punch that into your calculator, and again, you don't have to multiply it out to punch it in. You can punch it in exactly how it was right here. Just make sure you use the parentheses. When you punch that in, you should see something that looks a little bit like this. So we can see here, here's a turning point. That's a local minimum. Here's another turning point. So this does indeed have the maximum. It has 2 turning points. Now, where are the x-intercepts? If you want to find the x-intercepts, you have to find them on your calculator or by solving algebraically. I assume most of you are going to prefer to use your calculator. So remember that this is second trace, and then you're choosing the zeros. And you have to find all of them. If you look at the sketch, there are 3 x-intercepts. So you need to use your graphing calculator to find all of them. So on your graphing calculator, when you have that pressed in and graphed, so you might want to pause it for a minute if you don't have that typed in yet. But once you have that graphed, you want to find each of those zeros. So it doesn't matter which one you start with. I usually work from left to right, but you don't have to work from left to right. So if I'm using my little sketch here, if I want to find this x-intercept, I do second trace choice 2 to find the 0. Remember that left bound for this 0 is going to be here. That's left bound. Right bound is going to be there. So do your left bound, right bound. And hopefully I can get my calculator to actually get. I have to move my blinky an awful lot. It says that that 0 is -4. So -4, 0 is an x-intercept. Then I move on to the next x-intercept. Here's another x-intercept. So, and that is a really bad picture, by the way. I'm sure you can see it on your graph. Left bound, in this case, left bound is here, down here. Right bound is here because you're going left of the 0, right of the 0. And it says that that one is at -3. Again, my sketch is a very poor sketch. It was just very rough. But that is your other x-intercept there. And then there's one more over here. So repeat again, second trace choice 2, finding the zeros. In this case, for that particular 0, when you have, excuse me, left bound is going to be here, and right bound is going to be here. So that particular 0, your calculator should tell you is at +3. So that makes those pretty easy. Now we need to identify all local minimums and maximum, all the hills and valleys. If you look at your sketch in a standard window, you're not going to be able to see this top. So we need to adjust our window until we can find it. So it looks like it's going to be pretty high up there. So I'm going to adjust my Y maximum up to, say, 100. And I'm going to have it count by tens just because I need to be able to see it. And there I can. So I changed my window. My Y maximum, I made it 100 so that I could see my local mins and maxes. So to find your local min, that's second trace minimum. So you do second trace choice 3, and now left bound, right bound on the minimum just means if you're looking at your graph here, left bound of the valley, right bound of the valley is what it means when you're doing mins and maxes. So go to the left of the valley, then go to the right of the valley, have it guess, and hopefully it pops up for you a local min at -3.52, and the y coordinate is -3.25. So 5, 2, and 2, 5 are the coordinates of your local minimum. So right here, that's the local minimum there. Then we need to find the local max. Again, this is the one you couldn't see until you changed the window. Local max, you do second trace choice 4, so maximum, and it's the same thing. You go left bound of the maximum, right bound of the maximum. And this one's not going to come out evenly either. That's okay. When we're using our calculator, we're allowed to use a decimal. It tells me that that local maximum, the x coordinate is 0.85, and the y coordinate is 80.29. I'm just rounding all of these to the nearest hundredth. Now, describing the end behavior. If I look at the end behavior on my sketch, as I go to the right, I look here and it's going down, so -infinity. As I go to the left, my arrow is going up, so +infinity. All right, once you've got all your x-intercepts, your local mins and local maxes, you are ready to produce an accurate graph. Now, here's the thing. you're not going to be able to use the same scale on the x-axis and y-axis here because you're not going to be able to see all of the pieces that you need to see if you count by the same thing. We don't want our y's going to 100 or our x's going to 100 just because the y's do. So look at what points you have to graph and pick a scale based on that. So my x values, my x-intercepts, -4, -3, +3, -3.5, 0.85, those are all, if I count by ones, I'm going to be able to fit those. So I'm going to count by ones on the x-axis. The y-axis, I need to be able to get all the way up to at least 80. So in order to do that, I look and I say, okay, I could count maybe by 20s. You could even count by 15s if you wanted to, but we need to be able to fit it. So let's say I'm going to count by 20s. Whatever you count by on the top, again, that has to be the same on the bottom. You can't change in the middle of an axis. You can choose separate for x and y, but you can't change in the middle of an axis. So now I should be able to plot all my points. So x-intercepts, -4, 0. So one right here, -3, 0 right here, +3, 0. Now my local mins and maxes. My local min, -3.5, -3.25. So again, since I'm counting by 20s, that's going to be just barely below down here. So there's my local minimum. My local maximum, 0.85, so almost to 1. And I'm going up to just above 80, so 20, 40, 60, 80. So here is where my local maximum goes. Make sure you are looking at your calculator to get the accurate shape, but it comes from way up here, goes to my valley, crosses back up, and then hits the hill there, and then crosses back down. So there is my graph of that particular polynomial. All right, so let's try one more. Hopefully this will make sense after doing it one more time. So how many roots does the function have? Well, I look at the degree and it's degree 4, which means it should have 4 roots. How many turning points it has? Well, it can have a maximum of 3, but to find how many it actually has, I need to look at its graph. So you can go ahead and clear out the first graph and type this one in. So 2x to the 4th minus 5x cubed minus 4x squared minus 6. And again, you can start back in a standard window. We'll have to adjust accordingly in order to be able to see all the pieces. So when I look in a standard window at this graph, it looks something like this. So I notice that I can't see what's down here. So I'm going to need to decrease my y minimum so that I can see it a little better. They're pretty close, so I probably don't need to go down as far as I did on the last one. So I'm going to decrease my y minimum to -50 and see if that will get it all. Oh, and that more than gets it all. So I can even make it even a little less. Maybe I'm going to go down to -40 instead. And I'm going to put my sketch down here now. So here is my sketch. My x-axis is still in a standard window. My y-axis goes down to -40 here. But as I'm looking at that, turning points, those are local mins and local maximums. I see a local minimum right here. I see a local minimum here. And I see a local maximum right here. So there are indeed 3 turning points. So now I just need to find all of my specific information using my calculator. So x-intercepts, again, second trace, choice 2. I need to find the zeros. It looks like there are 2 x-intercepts. So 2 of them to find. So do your left bound, right bound. So I always start on the left. So left bound is right up here. Right bound is here of that particular 0. So that x-intercept your calculator says is about negative 1.16. Now on my calculator, the y-coordinate says 1.4 e to the negative 12. That just means 0 because that's scientific notation. If you moved that decimal point 12 places to the left, you're getting 0. So it's just telling you that it's an approximation. Negative 1.16 is my first 0. My second 0 is right here. So left bound would be here and right bound would be here. So go ahead and use your calculator to find that 0. And again, it doesn't come out evenly, but we're rounding here to the nearest hundredth, so 3.21. Again, the y-coordinate has scientific notation, but that is 0. So those are my two x-intercepts. Now I need to find all my local minimums and local maximums. There are 2 local mins. So we have to do the second trace minimum 2 times. So here's a local min. Here's a local min. So that's what I'm going to find first. So starting on the left side, second trace, choice 3, I'm going to find that local minimum. And so I'm going to go left bound of the minimum and right bound of the minimum. And it tells me that that local min's coordinates are negative 0.43 for the x and negative 6.27 for the y. Don't forget that there's a second local min down here, so we need to find that one. And it says that its coordinates are 2.31 and negative 32.01. That didn't show up very well. 32, here, let's just scratch it out and rewrite it. Negative 32.01. All right, so those are my local minimums. Then I have a local maximum right here, so I need to find that point. So second trace, choice 4, to find the maximum. And this one is telling me that the local maximum, my x-coordinate has the scientific notation, so that's 0. And the y-coordinate is negative 6, so 0, negative 6. Describing end behavior, if I look at both of my ends, both the ends are going up, which means both ends should be positive infinity, which should make sense because this is a positive function with an even degree. So now I need to graph it and choose my scale. So on my x's, the highest x I've got is my 3.21. The lowest one is negative 1.16. So I can certainly count by ones on my x-axis here. On my y-axis, my lowest point is negative 32. So I need to make sure that I'm getting down to at least that. So I'm going to count by 5s. Actually, I lied. If I count by 5s, I only get down to 30, so I'm going to have to count by 6s. So if I count by 6, negative 6. All right, so now plot my points. X-intercepts at negative 1.16, so just barely to the left of 1, negative 1 rather. 3.21 would be right over here. Local mins, negative 0.43, so like negative 1/2 almost, and then negative 6.27, so just below my first notch there would be negative 6.27. and then 2.31, so almost 2.5, and then all the way down to negative 32. So if I'm counting by sixes, that's negative 6, 12, 18, 24, 32, so just barely below this one right here. So there's my other local min. My local maximum is at 0, negative 6, so that's right on my notch there. And so now I just need to connect it with the correct shape. So it's pretty steep. So it hits a valley and then immediately comes up to a hill. And then it goes back down to hit a valley here, and then very steep increase back up. All right. So now we have produced a very accurate, very specific graph. So make sure you know how to fill all of this in and how to come up with the points on your calculator. That is all for today.